Hey everyone, so I know it's been a while, 3 weeks to be more exact, and well, college was having the best of me. Uh, I was actually stuck in some projects, not personal but from college, as I'm finishing it. So I had to put some time into that, and so I put the channel aside for a few weeks, but gladly I'm back so I can focus on it more, finish this IO library so we can go get into more interesting projects. I finished my script for the Rio mode bootloader, uh, teaching how to do a bootloader starting from Rio mode with using BIOS API system calls. So yeah, hopefully we can see a little bit more of that in the future, but now let's get to the video. So the last thing we did was print a new line and a character, and now I wanted to do this print unsigned integer, which is a very interesting project for us to do because it has a little bit it's quite tricky when we are starting with assembly, but once you get the hang of it, it's pretty cool. So here the definition says that the print uint, which is unsigned integer, basically a positive integer, outputs an unsigned 8-byte integer in decimal format. We suggest you to create a buffer on the stack and store the division results there. Each time you divide the last value by 10 and store the corresponding digit inside the buffer. Do not forget that you should transform each digit into its ASCII code. So that's it for our function. So I'm gonna go to Excalibur and draw some things so it makes sense for us, because I think it's very interesting, the approach and understanding this, what's going on, why we're using the stack here. It's very important for our assembly programming journey. So here's an example of a number. Imagine we want this number 1, 2, 3, 4 to be printed by our print string function. But the thing is, it's a number, and we can't actually print it like this because it won't print since we don't have the ASCII correspondence. The ASCII correspondence is the ASCII table actually is a table that maps values into digits, characters. So if we had, for example, RAX for a print system call, if you were to issue a print system call, and we would give the value hexadecimal 30 into our register that it will contain the value that it will be printed, we would actually have the value 0 be printed because the hexadecimal 30 is the representation of the 0 character corresponding to the ASCII table, which is what the hardware uses. Right. So before we actually get we can transform the whole number. We can't actually transform the whole number itself, so we need to get the separate digits from the number and then apply that conversion into the ASCII digit, and then we'll be able to print it. So a easy way to do that was for us to do the division by 10, and every time we divide by 10 and get the remainder, we would have the lowest digit of the number. So here I put a representation of the stack, which is basically what we're going to do. So every time we divide by 10, we get a remainder, we add the 30. This is basically saying, beginning from the hexadecimal 30, which corresponds to 0, so 31 is 1, 32 is 2 to the maps to the ASCII table. So starting from 30, we're gonna sum the digit we are actually looking at, and then we're gonna have the digit we want, right? So we sum up that 30, which is the initial digit we can say that, and then we push it into the stack. At first it will look like it's in a reverse order, but when we look at the stack pointer at the end of the iteration would be right here. So actually what we do now is pop from the stack and insert into a buffer, so we can call the print string function, and it works like that. So I've written here a few steps that we need to be aware of so we can proceed, right? So the first thing we need to do is iterate over rex. Why rex? Because it was the parameter that I determined that it will have the number that we want to print. So until rec is 0, so it will go to division every time until it's 0. So we're gonna divide RAX by 10 and get the remainder. And when we get a remainder, we're gonna add the hexadecimal 30 to the remainder value and push that value into the stack. We're gonna do that until RAX register is 0. So now, as we have the ASCII code for each number, we just gotta store the values in the buffer. So as we pop from the stack, we're gonna insert into the buffer in the correct order. And then at the end, we're gonna call the print string passing the buffer as the argument. Right? So with this in mind, let's go to our program and start writing some code. Okay, so we're gonna start by defining the print unsigned integer label, and the first thing I want to do is set up the stack frame, right, with this frame pointer. The frame pointer is basically or called base pointer, is a pointer that actually gives us stability while using the stack, because every time we push something to the stack pointer changes. So the offset of the thing that we were looking at also changes. So we want something fixed, of fixed length, so we can observe it correctly while we are messing with the stack. So the base pointer marks the beginning of the stack, the stack segment inside that function, inside that program. So for us to do that, the first thing we do is push the base pointer into the stack, and then we're gonna move the base pointer, RBP, into RSP. So now the stack pointer and the base pointer are the same, but every time we push, the stack pointer will change, but not the base pointer. The base pointer will still be pointing to the old base pointer, so that when we finish the function, we pop that value, and when we call the return, it will return with the old value of the base pointer, which is actually being used in the function that called print unsigned integer. Make sense? I hope so. If not, please comment. Now I'm gonna be proceeding with the function. I'm gonna move to RBX the value 10, and I'm gonna push 0 into the stack. This 0 is basically the null terminator, so the buffer can know that our digits ended. Since we don't have to worry about this being a digit, for example. Oh, but what if I have a 0 in the middle of the number? We don't have to worry about it, because every time we iterate through a digit, every time we divide by 10 and get the remainder, we do the transformation. So a 0 in our analysis will not be 0 by the time we compare it. It would actually be 30 hexadecimal. So that's why we don't have to worry about it, because it will already be changed. And then this comparison in the future will not affect our number, because the values will be already will be altered, right? So here I can call the loop function and this loop inside the print unsigned integer basically does some stuff. So first thing we gotta do, division. The remainder goes to the RDX register. So every time we come back to this loop, we gotta move the value 0 into RDX. So we just do an XOR to RDX. So our value is always 0. And then we're gonna do diff by RBX. So this will get the value of REX, divide by the value of RBX, which is 10, and RDX will give us the remainder. So here, the next step is we'll already add the 30 hexadecimal, right? So we're gonna add to RDX the 30 hexadecimal, and then it's ready to be pushed into the stack. So we're gonna do that. So we're gonna push RDX. So now is the break part of our loop, where we compare RDX with 0, and if it's not 0, if it's not equal, we go back to loop. But if it is equal, the thing we're gonna do is gonna move the RDI to the position of buffer, which is that buffer we defined earlier in the BSS section, because we're going to use it now. So this is the end of our loop function, and now we're going to be popping from the stack and storing into the buffer. So we have another loop for that, which I'm going to call pop loop, I guess. Store loop, better, right? So we have store loop. Just give some distance from this, and then the store loop will start by popping and passing the value to REX. So now we're gonna be retrieving our values from the REX, and as I mentioned before, they are already on the ASCII table format. So whenever we find a 0, it's because it is actually the null terminator and not a 0 character that wasn't parsed. So that's why we do this verification just now and not that time, because that time we already had the 0 on the stack, so we were pushing new things. And now as we're retrieving, we got to be careful with that, but we don't have to worry about it since everything is transformed, right? So we pop into the REX register, so we compare the value of REX with 0, and if it's equal, we pass into the print function, because it will already be fully finished. We reach the end of our string, of our number, right? So now I'm gonna move to the value of that position of RDI, which is pointing to the buffer. Now we'll receive REX. Now we're gonna increment RDI as a form of passing into the next position of our buffer. So as we increment this, we're gonna jump back into the store loop, and that's our store loop finished. Now for the print label, what we need to do is actually put a null terminator into the end of our buffer, and then return the RDI register, which is the parameter which we call the print string function, into the beginning of the buffer. So we'll reset the place it is pointing to, so we can print it correctly, right? So we basically do here move byte, passing RDI, and we insert a 0. So here separated, and then I'm gonna move RDI to buffer, which is the first position, into the buffer, and now I can call print string. And then we do the final cleanup, being removing the base pointer from the stack and actually returning to the function that called us, because we need to clear out, since we added that base pointer just for that function, and we didn't actually even use it here, but I wanted to talk about base pointer because it's a very important concept. But in the future we might use it somewhere in the code, and it will prove to be more useful than in this example right here, right? So now we gotta move our stack pointer back to our base pointer, which is the beginning of this, the first position that stack had during this function. We move it back to that, so everything that was in the stack, well, it's not, because we popped everything from the stack. So we're moving the stack pointer back to the base pointer, which is the first appearance in this function, and then we're gonna remove the base pointer. So now the base pointer, since it's pointing to the old base pointer, when we pop, it receives the value of that old pointer. So we're basically saying, okay, I'm ready to return, right? So here I do the return. And basically that's our whole function. So let's try it out now. So let me make all again, and let's run it, and it prints 1, 2, 3, and 4. Let's try with another example just to make sure. Let's say RAX gets us 4, 4, 5, 1. And then if we make all and call it, there you go, 4, 4, 5, 1. So that's how you print base 10 numbers in assembly, by using the ASCII table, 10 division, and that's it. I hope you guys enjoyed the video. I might keep up with this series, but it's not something that I'm totally willing to do. But of course, as I started, I went to finish because I feel like it's a compromise that I have with not only myself, with anyone that's watching this to learn more. But okay, that's it. So thanks for watching, and I'll see you in the next video. Bye.